continuing the part of operating system. So the topic is CPU scheduler today. CPU scheduler. So in the previous lecture, we discussed how why we need operating system, and also the problems we have if there is no operating system. So today we are going to discuss the topic CPU scheduler, which exists because multiple programs compete for a single CPU. So what does it mean by multiple programs compete for a single CPU? For example, if we have our computer, we bought a computer, we have a CPU in it, and then we install programs in it. For example, Spotify, Netflix, and let's say Chrome. And now we are running it in our computer. So which process gets the CPU? So we discussed what is a process in our previous lecture. So a process is nothing, a program in execution state. So program in execution state. So which program gets the CPU? So CPU scheduler decides that. The problem we are discussing is that, for example, if a program is running, let's say this is a CPP program, C++ program, and this program is running in our computer, and suddenly it needs user input. For example, we take user input using scanf in C++. So it needs now user input. We discussed it, humans and other devices like printers, etc., are slow devices, and CPU is extremely fast device. So now, if let's say human takes 3 seconds to write an input, for example, it can take any amount of time for a human to write an input, so we don't know. But let's say 3 seconds, if a human takes to write an input, that 3 seconds is a waste of CPU. CPU is sitting idle for the user to write an input. That should not happen, because CPU is extremely fast and we are wasting its potential by waiting it to uh, let the user write the input. That should not happen. CPU is expensive, and we should not waste it like that. And to give you an idea how fast the CPU is, modern CPUs comes in gigahertz, while the older CPUs came in MIPS, million instruction per second. So they used to million instructions per second. So they used to instruct million instruction per second. But now the modern CPUs are even more fast. They operate in gigahertz. So for example, 1 gigahertz is equal to 10 to the power 9 cycles per second. 10 to the power 9 cycles per second. So let's say for one cycle, how much 1 by 10 to the power 9 second it will take to complete one cycle, which is equal to 10 to the power minus 9 second, and which is equal to 1 nanosecond. So to complete one cycle, our CPU takes 1 nanosecond. It is so fast. And if CPU waits for the input, it is a massive loss of time for us. So we had to come up with a method to such that it doesn't waste the time. So let's discuss how CPU scheduler works. So first of all, there are criteria discussed, like how can we what can CPU do. So basically there are different processes happening inside our computer. Let's say P1, P2, P3. These are different processes that wants the CPU. We discussed that they all need CPU, these all programs. So let's say them P1, P2, P3, and they all need CPU. So which process gets the CPU? So CPU, there are different criteria for it. One criteria is first come first serve, FCFS, which is first come first serve. Whoever comes first will get the CPU first. And there are other criteria too. So for example, one who needs it for the shortest time will get the CPU. So there are different criteria for CPU scheduler. uh, let's discuss how what are the different components in CPU scheduling. So first is short term scheduler, STS, short term scheduler. So it decides which process will be executed next on the CPU based on CPU scheduler. And another is dispatcher. Dispatcher's job is to perform context switching. It performs context switching. Now, what is context switching? Uh, Context switching is basically, if let's say this is our CPU and P1 was performing in it, and suddenly there P1 has to wait for the input. Now we cannot let CPU sit idle, so we store the data we have in of P1 till now and bring another P2 to run inside the CPU. And when the input is entered, and then this P2 gets back and P1 comes back with its previous knowledge. There, this is known as context switching. And context switching is a massive overhead for the system. Overhead means it is a pure overhead to the system. Basically, overhead means wasted time where no actual process execution happen. So yeah, let's discuss how dispatcher, STS, and context switching work together. So basically, dispatcher takes the process's current data, such as process variable, general process registers, program counter, and stack value, and store them into process control block. It can resume its operation exactly from where it left off without losing data. So you can understand, like dispatcher just do, it stores the data which was happening inside the CPU into PCB. PCB stores process ID, PID basically, and program counter, CPU register, process state, and scheduling information. Link information. This is the complete information about CPU scheduling. There are two types of CPU scheduler. Types of CPU scheduler. Non-preemptive scheduling and preemptive scheduling. And preempting scheduling. Preemptive scheduling. So to differentiate between these two type of CPU scheduler, in non-preemptive scheduler, process willingly leaves the CPU. Process willingly leave the CPU. And also, CPU cannot be forcefully snatched away from the running process. Basically, if P1 is running, it will first happen complete, and then P2 will get the CPU. And in preemptive scheduling, if P1 is running and it is wait for the input, so then P2 will enter, and then again P1 will come. So that is how things work in preemptive scheduling. Whereas in non-preemptive scheduling, first P1 will happen complete, and then P2 will happen. So basically, preemptive scheduling is more efficient. For example, if a process with higher priority arrives, it will happen first, and then the other processes happen. So this is how two types of CPU scheduling. Now we are going to discuss a list of CPU scheduling algorithms. So first come first serve. Whoever comes first will gets the CPU, and its preemptive version is called round robin. Round robin. This is the preemptive version of FCFS. Uh, these are non-preemptive version. These are preemptive version of them. Okay. Another one is shortest job first or shortest job next. Basically SJF or SJN. Their preemptive version is called longest remaining time first or longest remaining time next. LRTF or LRTN. And third is priority scheduling. It can be both preemptive or non-preemptive. And the last type is multi-level feedback queue. Multi-level feedback queue. Now, first we are going to discuss it first come first serve. So it is clear, and I told you that too, that whoever comes first will get the CPU first. So basically, first of all, let's just get over with the general terms we are going to use in first come first serve. That is PID, which is process ID, and burst time, arrival time, so process ID. Uh, the OS identifies every process by a unique number known as its PID. So it is just how different processes is identified by the operating system. So the OS gave them a PID. And burst time. It is also known as CPU burst. CPU burst. And it is the amount of continuous CPU time a process can take. Like how much time a process takes in the CPU, not how much time it waits for the CPU, but just how much time it gets the CPU is known as the burst time. Arrival time. Arrival time is the exact time a process enters the CPU. Time a process enters the CPU. The CPU. We do have a question. We do have a question here. That is, what if two process enters at the same time, P1 and P2? Let's say their arrival time. Arrival time is both 0 second. Let's say they both came together. So who will get the CPU? So now whoever has a lower PRID, like smaller PRID, will be executed first in the CPU. So that is a tiebreaker rule. Tiebreaker rule. So we understood that what is PID. So basically how operating system identifies different processes. Burst time is how much time a process gets in the CPU. Arrival time is when the process enters the CPU. So now we are going to discuss some more terminologies, which are first is TAT. And TAT stands for total. One second. TAT stands for turnaround time. Turn around time. So turnaround time is nothing but total time process spent in system. The total amount of time the process is spent in system is known as turnaround time. So the formula to calculate TAT is process finish time minus process arrival time. It is a very important formula, and to identify process arrival time is generally given in question. given in question, and process finish time we will identify by Gantt chart. Gantt chart. So the next term we are going to discuss is waiting time. Waiting time is nothing, just the total time process is spent. Total time process is spent waiting for the CPU. Spent waiting for the CPU. So the formula for waiting time is just turnaround time minus burst time. So basically, the turnaround time consists of the total time. If we reduce the time the CPU, the process is spent in the CPU, we will get the time the process waited for the CPU. That is simple because it is a non-preemptive version. Another term we are going to discuss is response time. Response time is the wait before a process gets the CPU for the very first time. So the response time is equal to process start time minus process arrival time. Basically, the wait before a process gets the CPU. So for non-preemptive, which we are discussing right now, response time is equal to waiting time. Because when a CPU gets the in non-preemptive, when a CPU gets the when a process gets the CPU, it will executes completely. Therefore, for non-preemptive, response time is equal to waiting time. Response time is equal to waiting time. Yes. So now next term we are going to discuss is throughput. Throughput is number of processes completed per unit of time. Basically, a number of processes divided by total completion time. Total completion time. Another term we are going to use is CPU utilization. So it is a percent of test of time CPU was actively working. Formula to calculate CPU total burst time divided by total completion time. Multiplied by 100. The last terminology we are going to discuss is convoy effect. Basically, FCFS is fair but not efficient. For example, if we have three processes P1, P2, P3 and their burst time is 100, 2 and 2 and arrival time is 0, 1, 2. Now P1 will be executed first and then P2 has to wait for 100 seconds and P3 has to wait for 102 seconds. So why they are waiting so much second if they just need to work 2 seconds? So it is unfair for them. So therefore FSFS is fair but not efficient. So that's it for today's lecture. Thank you.